I just want to say a few more words about acetylcholine. If you refer to the overhead on acetylcholine, you can see that it says here, it's the a neurotransmitter that is found at the neuromuscular junction. That is in the peripheral nervous system, where motor neurons come out, right, and meet, across a synaptic gap with muscle cells, right? And the release of a neurotransmitter will provoke contraction of the muscle. Well, the neurotransmitter that's released at this junction between the end of a neuron, the axon of these neurons, these motor neurons, and the muscle, is acetylcholine. So acetylcholine is a very important neurotransmitter in the periphery because it's very important for promoting contraction of muscles. It's the neurotransmitter found at the neuromuscular junction. In the central nervous system, acetylcholine actually plays a pretty important role in cognition. And one way to sort of kind of emphasize this role is to let you know that the drugs, the only sort of FDA-approved drugs that are basically prescribed to slow the progression of some of the memory and other cognitive losses associated with, for example, Alzheimer's disease and other dementias, tend to be drugs that inhibit acetylcholine esterase. So they target that ache. These are drugs that bind to acetylcholine esterase in the synaptic cleft, and they, when one chemical binds to another, they change shape, right? It prevents acetylcholine esterase from carrying out its normal function, which is, of course, to break down acetylcholine. So by inhibiting the enzyme that breaks down acetylcholine, these drugs actually lead to an increase in the amount of acetylcholine that lingers, that stays in the synaptic cleft whenever there is, some kind of acetylcholine release. And this kind of increase in sort of signal strength, basically, has been linked to a slowing of the decline in some of the cognitive faculties, particularly in memory function, in those with dementia. This is not a cure, but it indicates that acetylcholine plays a relatively significant role in cognition. I should mention also that some poisons also target that acetylcholine esterase a degradative enzyme. There are a number of poisons actually that bind to it irreversibly. These drugs that are potentially therapeutic here actually bind and then release, bind and then release, but there are some poisons that bind permanently. Some of these nerve gases, for example, like sarin gas, bind onto acetylcholine esterase and don't let go. And they change its shape so it cannot perform its normal function. It cannot break down acetylcholine. And what you get is increasing amounts of acetylcholine and much too much stimulation of the postsynaptic membranes, particularly in the periphery, in the muscle, right? So the postsynaptic receptors for acetylcholine are very interesting. The nicotinic receptors are actually ionotropic. You should know, for example, if it's called nicotinic, it means, a particular chemical binds there. In this case, it's nicotine, right? And it's ionotropic and opens a depolarizing current so that, sodium comes in typically. And if sodium comes in, you get muscle contraction. If you overstimulate, with too much, acetylcholine, overstimulate that receptor, it'll keep, opening, and then eventually it shifts into this other shape. If it gets too overstimulated in too short a time, it shifts into another shape where it cannot be reopened again for a little while. It goes into this other conformation, this other structural form, and we refer to it as being desensitized. It's not sensitive anymore to acetylcholine. So, sarin and these other kinds of poisons, bind to acetylcholine esterase, right? And they result in an increase in acetylcholine in the synaptic cleft, so much more stimulation of these, receptors, these ionotropic receptors, and then these ionotropic receptors, when they're overstimulated, they shift into this form where they no longer respond to any acetylcholine at all. So you get this, with these gases, intense sort of rigidity and contraction initially, and then no responsiveness, of muscle to nerve. And this is, of course, deadly. For example, people can die of asphyxiation when the diaphragm muscle no longer responds to signals from the central nervous system, to contract and allow for breathing.